All right, let's dive right in. We're going to talk about something that might sound like a dry math topic, but I promise you it's the hidden code running underneath, well, pretty much everything you interact with. We're talking about the matrix. Think back to algebra, right? You've definitely seen a problem like this. It's a classic puzzle. And sure, you could solve it with some substitution, but what happens when it's not just two equations? What if you're dealing with hundreds or even thousands? You're not going to solve that by hand. You need a much more powerful, more organized way to handle it.
And that's where our hero for today steps in, the matrix. Look, at its heart, it's just a simple box for numbers, a grid. But don't let that fool you. This simple container is the key to wrangling huge, messy problems into something clean and efficient.
So check this out. We can take that jumble of equations and just sort it. It's so satisfying. All the numbers in front of the variables, they go into one matrix, which we'll call A. The variables themselves, x and y, they get their own little matrix X. And the answers on the other side of the equal sign, they go into matrix B. And just like that, boom, multiple lines of algebra become one single beautiful equation, AX equals B. Now that is an upgrade. Okay, so we've got everything neatly packed away into these grids. But now what? What can we actually do with them? Let's get into the rules of the road. I mean, sure, you can add and subtract them. That's pretty straightforward. But the real magic, the operation that lets us do all the cool stuff, like transforming data and solving these huge problems, is multiplication, and it follows its own very specific, very powerful pattern. And that pattern is all about a rhythm. To get each new number in your final matrix, you multiply a row from the first matrix by a column from the second one. You just move across the row and down the column, multiply the corresponding numbers, and then add them all up. It's just row on column, row on column. Once you get that little dance down, you've got it. Now, this is where it gets really interesting. It turns out that every square matrix has a secret hidden inside of it, a single number, a kind of secret code that tells you an incredible amount about the matrix itself. And we call it the determinant. This brings us to a really important question. We've got our elegant little equation, AX equals B, but how do we know if it even has a clean, single answer? Is there a way to check before we do all the work? Is there some kind of secret key that tells us if this puzzle is even solvable? Yes, there is, and it is the determinant. Honestly, you should think of it like a quick diagnostic test for your matrix. It's one special number that you calculate from all the numbers inside, and its value is a very, very big deal. And for a simple 2x2 matrix like this one, finding it is super easy. You just multiply the numbers on the main diagonal from top left to bottom right, and then you subtract the product of the other diagonal. That's it, A times D minus B times C. And that one little number you get tells you something profound. And here it is. This is the crucial insight. If that determinant is anything other than zero, you're golden. Your problem has a single, unique solution. The matrix is called non-singular. But if that determinant is exactly zero, game over. There is no unique solution. The matrix is singular. This one number is literally the gatekeeper that tells you whether you can even move forward. Okay, so the determinant gave us the green light. We know a solution exists. But how do we actually find it? Well, that brings us to the ultimate tool that the determinant unlocks, the inverse matrix. You can think of it as a matrix's very own undo button. And you only get to use this amazing undo button if the determinant isn't zero. See how it all connects? Our diagnostic test came back positive, which means we're guaranteed to have this powerful tool at our disposal. It's called the inverse, and it's how we're going to finally crack this thing open. So the inverse, which you write as A with a little -1 up top, has one incredible property. When you multiply any matrix by its own inverse, they basically cancel each other out. What you're left with is something called the identity matrix, which is just the matrix version of the number 1. It's the ultimate reset button. And this right here is the golden rule that ties everything we've just learned together. A matrix has an inverse if and only if it is non-singular. And what does non-singular mean? It means its determinant is not zero. It's a perfect logical chain.
Okay, time to put it all together. We have our tools, we know how to organize the problem, we know how to check if it's solvable with the determinant, and we have our magic undo button, the inverse. Let's go back to that original puzzle and finally solve it. So here we are, right back where we started. Our nice, clean equation, ax equals b. The whole goal is to figure out what's inside matrix X, our unknowns. We need to get X all by itself on one side of that equal sign.
And this is how you do it. It's so unbelievably elegant. To get X alone, you just multiply both sides of the equation by the inverse of A. On the left, A inverse times A just poof, they cancel out, leaving just X. And on the right, you're left with A inverse times B. All that algebra, all those concepts boil down to this one beautiful formula. That's your answer.
So why does any of this matter? Is this just a neat trick for your old algebra homework? No way. This grid math is the engine running our entire modern world. I'm talking about the 3D graphics in every video game you've ever played. This is how data analysis and machine learning models work. It's used in cryptography, in securing your communications, in modeling the economy. It is everywhere. This isn't just theory, it's the practical language that computation speaks. So the next time you see a really complex problem, a network of relationships, or just a massive, messy data set, ask yourself, could this be a matrix? Because now that you understand the language of these grids, you have a powerful new lens for seeing the hidden structure that really truly runs our world.